Thank you. Okay, good afternoon. I'm going to discuss some fairly recent work that I've been doing, mostly unpublished at this point, in the area of the interaction of light and ultrasound, pretty much in highly distorted media. So let's, I didn't, wait a minute, whoops. Okay, so I want to talk just briefly about light scattering, and I'm going to show you this little example. Basically, light entering a disordered medium scatters and spreads itself pretty much throughout the medium. And one of the questions that we can ask ourselves is there any memory of?
Did you do that yourself?
I did that myself, yes. Is there any memory of where those photons came from? We know that with the diffusion of light, although we can make measurements down to optical resolution at shallow distances in tissue using confocal microscopy, OCT, and other techniques, at greater depths we're limited by the scattering to resolution that gets up into the millimeters. Ultrasound, on the other hand, doesn't have this problem to such an extent, and while the depth of penetration increases with decreasing wavelength, the resolution ends up being always wavelength limited. So there's a region where the ultrasound actually works to a higher resolution at a greater depth than does light. So can we combine the two techniques to retain the best benefits of each? Okay, there are several things we could do, and different groups are doing a lot of these. One is to just use take an optical image and an ultrasound image and use them somehow synergistically. Put the two images together and see if we can learn something that we can't from either one separately. Another area that's been very successful of late is photoacoustic tomography, basically introducing a pulse of light into the tissue to create an acoustic wave and measuring that with an ultrasound detector. Photothermal tomography, we heat the tissue and we could measure again with some sort of a motion detector. Sonoluminescence, we generate light with sound. And the topic of today's talk, ultrasound modulated optical tomography, where we modulate the light with ultrasound and detect the modulated light. So basically we put some light, possibly a CW laser beam, into our medium and some ultrasound. And at the output, most of the light that comes out will be unmodulated. Will have the same temporal characteristics as the source, delayed a little bit. And some of the light will be modulated by the ultrasound. We know that that light passed through the ultrasound wave somehow and was affected by it, so we know something about where that light has been. We say that the light is tagged by the ultrasound, modulated by the ultrasound. This goes back to less than 2 decades. The first experiments in this area were done at GE by Brooksby and Murray Penny, and published in 1995. Shortly thereafter, Li Hongwang published his ultrasound modulated optical tomography. I'm using his title to describe the effect. And following that, there was a lot of work to increase the strength of the signals. There was work detecting multiple speckles and trying to do some sort of parallel detection. There was a very large high-finesse Fabry-Perot interferometer that actually separated the modulated light in frequency. Keep in mind it's only a few megahertz displaced from the carrier. And some work in our group and another group on the use of a photorefractive crystal, which is predominantly what I'm going to talk about today. to detect the modulated light. More recently, there's been some renewed enthusiasm in this field in the area of phase conjugation and delivery of light into tissue. Okay, so let's look at what happens when light interacts with ultrasound. In a clear medium, we know fairly well what happens. We use Maxwell's equations, which are a coherent description of the light waves. We expect diffraction-limited imaging, and the effect of ultrasound is the Bragg effect. It basically acts like a moving grating, spreads the light into different orders, each one at a integer, shifted by an integer multiple of the ultrasound frequency. At the far end here, in a highly turbid medium, we can't really use Maxwell's equations effectively. We use radiative transport, which is an incoherent description of light. We use the workhorse equation as the diffusion approximation, and we do imaging in terms of photon migration, diffusive optical tomography, photon density waves, and so forth. The interaction of light and ultrasound here is considerably more complicated. That's what I'm going to talk about. In the intermediate area, we should remember that there are materials that are somewhat scattering, but not so scattering as these highly turbid media. And in that case, we have to have a theory that's somewhere in between. Okay, so let's look at how light and ultrasound interact. Okay, there are several different mechanisms. I'm going to talk primarily about the first two on this little cartoon. Let's actually get the second one here first. One thing that happens is that as the ultrasound pressure increases, the material becomes more dense, the index of refraction goes up, and the light that is scattered through that portion of the medium travels a path which is optically longer. The optical path length, n integral of index of refraction dl, is increased. Okay. Another option is that if a scattering particle moves, the physical length of the path changes. Okay, the physical length is going to change according to the component of the displacement that is along the delta k vector for the scattered light. So in this case, it would be the small component of the displacement that's in this direction. The path now becomes physically shorter or longer as the particle moves back and forth, and this happens at the ultrasound frequency. So in these two mechanisms, the phase of the scattered light that follows that particular path is modulated by the ultrasound at the ultrasound frequency. Other options that are probably less important, size or shape of the scattering particles. For example, if you have microbubbles as an ultrasound contrast agent, those will physically change size and will therefore change their scattering coefficient. So there's a delta sigma effect which will actually make a change in the amplitude of the light that's scattered along that particular path. Less commonly thought of is radiation pressure. Okay, in optics, it's fairly hard to generate radiation pressure. You can levitate a micron-sized bead in a fairly powerful laser beam, but it's not the easiest thing to do. Ultrasound, it can happen much more easily. And so now what happens is have an effect that is not at the ultrasound frequency, but the displacement is subject to a force caused by the ultrasound in the direction of ultrasound propagation. And I can get some fairly large displacements in that. If you put your hand in front of an ultrasound transducer, you can feel it. Again, we could have a change in the index caused by a change in temperature. Ultrasound heats the tissue, and there'll be a change in temperature. Again, not at the ultrasound frequency. This will be just an overall change in temperature. And finally, this is the mechanism that I thought was important when I first heard about this effect. As the particles move, there will be regions where the particles come closer together, increasing the density of particles with a given scattering cross-section will increase the scattering coefficient and thereby increase the diffusion. And so I thought of this idea of modulating a diffusive wave. It turns out that effect does exist, but it's extremely small and not a very good thing to use. Okay, so here's a little more detailed look at what happens. If you've ever done any kind of Monte Carlo modeling, you've seen pictures like this where the light travels along highly scattering paths through the material. One of these paths, the white one, happens to go fairly close to the ultrasound focus, and so the interaction there will be fairly strong. If I zoom in on that little region, you can see this white path. I've actually drawn two paths, one that has an extra scatterer in it. As the scatterers move and as the pressure changes the index of refraction, these optical path lengths are going to change. They're going to change in unpredictable ways, depending on exactly where I go through the ultrasound and what direction the motion is. So although there's a change in the optical path length that is at the ultrasound frequency, the phase of it is going to be fairly unpredictable with respect to the ultrasound frequency. By the way, I should mention that the optical path length changes that we're talking about here, around a megapascal of ultrasound pressure, turn out to be in the single-digit nanometers. And depending on such things as frequency and the type of the material, the scattering effect or the index of refraction effect may be dominant. So the computational model that we're going to use is that the electric field contribution from one path, this white path, for example, is some constant A that represents how much light follows that path, and the phase term, which has the optical carrier, and the integral of NDL over the path, which are broken up into a background NDL and a delta NDL, a small change. And I'm going to represent that change as just m cosine of omega ultrasound t. So it's a sine wave at the acoustic frequency with an amplitude m. And that, by amplitude there, I mean a phase shift m, which will be typically something in the milliradians at the strongest. Okay, so let's look at this in the complex plane. The center of the plane is right here, 0, 0, 0, and the electric field is just a phasor that's moving back and forth like this, keeping the same amplitude but varying its phase. Okay, now if you look at FM radio signals, you know that the Fourier transform of this will be given by a set of Bessel functions right here. Okay, I've expanded, by the way. I've written this cosine in terms of its exponential form, and then I've allowed the m to be complex, so I can introduce a phase on that as well with respect to the ultrasound. Okay, so let's take a look at this Bessel function, or alternatively, because the modulation index is small, the phase shift is very small, I can just take this equation and expand it in the Taylor series. Okay, and the zeroth term will be just the value 1 in this case. The first term will be proportional to m, proportional to the modulation. It'll be orthogonal to the carrier field itself, and it's equal to j times a times m. Okay. If we look at the second order terms, there are actually two. One comes from the zero order Bessel function, the second term of the zero order Bessel function. The other one comes from the first term in the second order Bessel function. Okay, we get a second harmonic, which is proportional to m squared. And the optical carrier is modified by an amount m conjugate. Okay? And this is important because if you look at the second harmonic, it's going like m squared. That's basically what in the second order term is causing the curvature here. This term is always a positive number. It's preceded by a minus sign. So it's always reducing the amplitude of the carrier. again, FM radio engineer knows this well. The carrier is reduced as energy goes out into the other sidebands. Okay, so if I look at this, basically look at the average of a field that's moving along this blue curve, and it's going to be right there where the green dot is. If I'm only going to second order in my Taylor series expansion, the curve is actually the cyan line, and the center is at the magenta cross. Okay, these are very close together, and I've really seriously exaggerated the value of m in this picture. So the bottom line is we're okay looking at the spectrum of the modulated light only out to the second order in the modulation term, only out to the second harmonic of the ultrasound. Okay, question.
So the phase of the first harmonic is 90 degrees. The phase of the second harmonic.
Okay, let me go back to that for a minute. Right, the first harmonic basically just describes the phasor moving perpendicular to its own direction. Okay, so the change in the electric field is up and down on the page if the nominal value is horizontal. Okay, the second order term basically moves it this way. Okay, and so that's a real term multiplying the A. Now in reality, the amplitude of this wave itself is a complex number, so it could be anywhere in the complex plane. So everything here is all multiplied by that value of A. And we'll see that that becomes important shortly. Okay. So for a single diffusive path, here's the first order term, JAM. And for multiple paths, K, we need to sum over the multiple paths. Okay, now the issue is that when we sum over multiple paths, A sub K is a random number. It depends on the length of the path, the optical length of the path from the source to the detector, which is millimeters, maybe more, and certainly many, many wavelengths, and is in fact a random number. M is also a random number because we don't know where that path went through the ultrasound. Okay, so we don't know whether the phase, what the phase of M is with respect to the original ultrasound wave. Okay, so therefore, this is a complex random number, zero mean, and the result is incoherent summation, which gives us a small result. Okay, in contrast, if we look at the carrier, the nominal value of the carrier is just A, and it's a complex number, and the amount by which it is suppressed is m times m star. Again, as I mentioned, that's a positive number. So when I look over multiple paths, A sub k again is a random number over m sub k, mk star. Although it's a random number, it's always positive. It's not completely random in phase. The result is then that these will, in some sense, add coherently. If I can mix the signal ultimately with a reference wave that goes like A sub k, I will end up with a number which will be definitely negative, and I can then average over as many paths as I want, and that number will keep increasing, and it will increase now linearly in the number of paths rather than like the square root. Okay, so trying to understand this phenomenon better, we chose to use a technique we call computational microscopy, in analogy with computational electromagnetics, and to basically generate synthetic images that we can take apart and analyze in a way that we can't do real experiments. Okay, everything is done in MATLAB. It's a very simple finite difference time domain algorithm. Our students all learn it in their computational electromagnetics class. Some of the undergraduates even learn it. They have this simple MATLAB code. And all we did is expand it a little bit, run it on a cluster machine so that we can do multiple runs at the same time. The first person that I know that used this in biomedical optics was Andy Dunn, who was looking at the light scatter from cells as part of his PhD back in 1996. Later, Andy collaborated with us, and we looked at images of embryos using a phase measuring microscope that we had invented. The idea here, this figure was showing that we could computationally focus through an embryo that had 3 cells inside it, and that depending on where we were focused, we could see the individual 3 cells. Later, we used it for a bistatic confocal microscope with a split aperture, looking at imaging of skin, a very detailed model of the epidermis in skin. And most recently, we've been using it with some of our mechanical engineering collaborators who are interested in the mechanical properties of lung. And what they do is they push on the lung with an indenter. The indenter has a plastic tip with an OCT system behind it to do imaging. And these synthetic images, this is a mechanical model of how the lung will deform. And these are synthetic images generated from the mechanical model. They look surprisingly like the images that we actually collect in the lab. So we took this computational technique and decided to extend it to look at the ultrasound interaction. Briefly, if you're not familiar with FDTD, what happens is in Maxwell's equations, we have a space derivative of one field equal to a time derivative of the other field, and vice versa. So if we replace the derivatives by finite differences and arrange our little volume cells of electric and magnetic field components appropriately, we get an equation that looks like this. We take some space derivatives of h, and that generates a time derivative of e. So if we know what e is now, we can predict what it will be in the next cycle. And then we could replace this equation with the a's and h's swapped, and constants are different, and do the same thing again. And so we basically go around this loop, starting from initial electric fields and some configuration of the system specified by its index of refraction. Take the space derivative of the electric field, compute the time derivative of the magnetic field, compute the next magnetic field, then reverse the process, come back, get the next electric field, and just go around again. And as we do, we generate a movie of the propagating electromagnetic wave. And we're doing this now in 2 dimensions for computational reasons. It gets very computationally expensive to do large volumes in 3 dimensions. And we actually do frequently make movies of the propagating electric field. The outputs that we get are the field quantities. And at the very end of the calculation, we take the Fourier transform of the last few cycles. So we now have a complex representation of the electric field and the magnetic field. Okay? From that, we can take the magnitude squared, divide by z, the impedance, and some people call it eta, and divide by c, the speed of light, and we'll have the energy density, watts per cubic meter. If we don't divide by c, we have the irradiance, watts per square meter. All right? And if we take E cross H, we have the Poynting vector. Okay? And in the case of a plane wave, the magnitude of the Poynting vector is equal to the irradiance. Okay? In a diffusive wave, the energy density is calculated the same way. We have this quantity that has power per unit area units, which we call the fluence rate. And in this case, the pictures are going to look more ugly. I'll show you some examples of them. When we compute the Poynting vector the same way, we get a number which is generally less than 5, sometimes a lot less than 5. In a good diffusive wave, it will be a lot less than 5. And in fact, according to diffusion theory, it's given by d times the gradient of phi. So these are the quantities that we can look at. I'm going to show you some pictures of these as we go through the numerical examples. I think I just skipped 2 pages. Okay. So let's make a scattering medium. For the time being, I'm not going to try to make it look anything like tissue. I just want something that scatters a lot of light. And so this could be some model of some scattering medium of index fairly high, 1.42 in water, and the scatterers are just randomly positioned and given them a certain size, and they exist between 20 and 80 microns on this vertical scale. Now what I've done is I introduced a plane wave from the top, and in this square region in the middle, I looked at the propagation of that plane wave. I basically just mixed it with a plane wave and took that mixing term. So I get rid of all of the scattered light. I'm just looking at the unscattered light. Okay? And if I plot the change in amplitude, I can get mu, the extinction. Came out to be a little over 500 per centimeter. And if I look at the phase, I can get the effective index of refraction of this material, which came out to be about 1.40. Turns out if you average the index of refraction in this region, you get a little bit smaller number, about just under 1.39, but fairly comparable to the 1.40. Okay. So we have a medium here that's not quite index matched. The index out here is water, and the effective index of this medium is a little bit larger. Okay, so let's introduce a narrow probe beam, a couple of microns in diameter, into the medium, and that wave propagates like a nice Gaussian wave in the clear medium. And when it hits the surface, some of it gets reflected, as you would expect. There's a slight index contrast there, remember? And a lot of it gets scattered, and you can see that as you get into about a little more than 5 microns, most of the light has been scattered out of the Gaussian wave. And if you squint a little bit, you can almost see circular shapes here, indicating that we have a good diffusive wave that is propagating from this point source. I'll show you a numerical example of this a little bit later on. Okay, by the way, these are dB, ranging over some 5 orders of magnitude. If I look at the Poynting vector, I need to explain the color scale here. Poynting vector has magnitude and direction, and so the color scale is here. The brightness moving out is a measure of the magnitude, and the color indicates the direction. And so here's the Poynting vector is pointing down, and the magnitude is very close to e squared over z. As we get into the medium, you can see that the Poynting vector becomes quite random, but generally speaking, on this side it's moving to the left, on the right it's moving to the right, and down below it's moving more down than up. Up above it's actually moving more up than down. And then of course once you come out of the scattering medium, it just continues to move in whatever direction it's moving. The light actually begins to become more coherent again. You can see that as well down at the bottom. You can see that all of the light is continuing in the downward direction. Okay, so this is the information that we have to work with. How do we get the ultrasound in?
What's the scattering length in that again? What's the single scattering length in that?
I'm sorry?
The scattering length?
The scattering is
the scattering length?
The mu is 500 per centimeter.
500 per centimeter.
Okay, so it's about a 20 micron scattering length. And so actually one of the things that I haven't done yet, I've gotten the mu out of this. One of the things I haven't done yet is to go back and get the mu sub s prime. I get it probably from that picture and see if I can then have the anisotropy, and then I can think about designing different media that will have properties that I want for the more computational experiments, as well as having some comfort level with the relationship of the experiments to the computational experiments to real experiments, which I hope to be doing soon, if the NSF is good to me. So how do we handle the ultrasound? Ultrasound has a whole different time scale. Okay? Sound travels at about 1,500 meters per second in tissue. So we can't do FDTD. Okay? I'd love to sell the computer that would do it, but we can't do it. But fortunately, remember that I said the only thing that matters at this modulation index is the first two sidebands. Okay? So we essentially have a band-limited signal. All right? And Nyquist tells us if we have a band-limited signal, we only need to sample at twice the highest frequency. And so it turns out that what I need are 4 samples of the ultrasound. It's hard to see in this picture, but each of these waves is displaced, I hope, by 1/4 of a cycle from the one before it. We collect the 4 samples, and then we solve for, in this equation, E0, E1, and E minus 1, the positive and negative sidebands. And we can also get the second order one, which we don't use. Okay? So basically what we have to do is, instead of actually running through the whole ultrasound wave, we just take 4 samples of the ultrasound and run them as 4 separate simulations on 4 different computers, put them back together at the end. Okay, here's the modulated probe. This is the light that you would see at the ultrasound frequency. This is in the previous page. This is E1. Okay, the ultrasound is focused here. I reproduced that just so you can see where it is. Remember, this comes from 4 samples that I'll put back together to make the diffusive wave. And you can see that the light is coming more or less from the ultrasound focus. It shifted a little bit to the left because, remember, our input source was coming a little bit from the left. Okay? And likewise, the pointing vector appears to be diverging from a point somewhere here, which is roughly the center of this picture. So we've nicely captured the signal, the modulated portion of the signal. And of course, what we want to do is to detect that down here at the bottom, or maybe back up here at the top in an epi detection mode. Okay, let's just take a look at this in comparison to diffusion theory. It's rough, but it does seem to give the right answer. Here is a different source. It is actually a slightly different medium. The light is coming into the medium, scattering, and what I've done is I've just assumed that it scatters from this point at 35 microns, and I've used the extrapolated boundary condition that everybody knows, I think, to predict the diffusive wave, the phi, and it looks like this. And it's not exact, okay, it seems to be a little too strong here, but basically it captures the general shape of the result. Okay, no fitting was done on that. I actually took the laser power that was used in the simulation, put it right there, and just let the results come out however they would. So I was relatively pleased with that, plotted on the same color scale. Okay, then I look at the modulated wave. It appears to be centered here, so I assume that it was centered here. And this, I just used this one source and generated the wave. I did fit this one so that the colors in the corners matched. Okay? And I found that in order to fit that, I needed to say that the power in the shifted wave is equal to the fluence rate in the unshifted wave multiplied by what you could call a scattering cross-section of 8 microns. Remember, it's linear units because it's only a 2-dimensional model. Okay? The ultrasound wavelength here was 15 microns. The index of refraction variation at the maximum was 10 to the minus 3. And so we got a fairly good conversion from the incident to the diffusive wave. No, that's what I wanted. Okay, so here was our first attempt at looking at the modulation of a diffusive wave. Remember, at this point, we really thought that what we were seeing was a modulation of the diffusivity. So we generated a diffusive wave at 70 megahertz plus a couple for the ultrasound, modulated a laser, passed it through a tank with an ultrasound transducer at the acoustic frequency, collected the light with an APD, passed it through a filter to collect, in this case, the lower sideband, amplified it, sent it to a demodulator where we demodulated it with 70 megahertz and collected the signals. And we sat in the room very quietly and integrated for a long time, and we did get some results. They were weak, but they were measurable. We actually showed, we were using titanium oxide particles in water, we actually showed that the signals depended on frequency because of the inertia of the particles. But we realized we were never going to do anything with this in any practical way because the signals were so weak. We were using single speckle detection. Okay, so the name of the game became how to increase the signal. Okay, we started with a high coherence source. We used coherent detection. We decided to use the carrier suppression wave rather than the first sideband so that we could get the advantage of coherent integration. That allowed us to do spatial averaging. And in order to take advantage of the spatial averaging, remember there was still an A in the equation, A sub k in the equation. That is, the unmodulated light wave is still in the equation. We need that as a reference. And so we shaped the reference wavefront to match the unmodulated wavefront so that it would mix efficiently with the modulated one. Okay, so briefly what we did was use a photorefractive crystal to make a dynamic hologram. And I think everybody knows in a hologram you mix a reference with an object on a plate of film. The interference pattern is the irradiance, some of the squares of the fields, some of the fields squared, I should say. And that irradiance exposes the film, or in this case, sets the index of refraction of the photorefractive crystal. Okay? When we process the hologram, we play it back with a playback wave, and if that playback wave is matched to the reference, then we detect an image which is proportional to the object, scaled by r star, and we can make r star very large because it's a reference wave that we control. And so we can actually make this image an amplified version of the object. We also get a ghost image in a place that we don't worry about. Okay, so here's the experimental setup. A 532 nanometer laser, frequency doubled YAG, test tank with a acrylamide phantom in it, and a photorefractive crystal detector assembly. The layout looks like this. The ultrasound is pulsed. We generate about 10 pulses of, in this case, 1 megahertz ultrasound. The transducer is focused. The laser and detector are set up in a Mach Zehnder interferometer, except for the fact that the recombining beam splitter is replaced with a photorefractive crystal. The photorefractive crystal remembers the wavefront before the ultrasound is turned on. The ultrasound is a very low duty cycle, and the photorefractive crystal has a long time constant, so it records that wavefront and delivers that signal to the detector. Okay, meanwhile, when the ultrasound is turned on, the modulated signal also falls on that detector, and we detect, mixing that with the reference signal, we detect that MM star term that I showed you earlier, which is, we're calling it now carrier suppression. And we didn't at the time that we did it. What you see at the detector is, if the ultrasound pulse looks like this is actually measured with a hydrophone, the detected signal looks like this. You don't see the modulation. Okay? What you see is a dip in the signal. Okay? Initially, I expected to see the modulation. And I started doing some calculations, and I said, wait a minute, that phase is random. It's going to add incoherently. I called a meeting, got all the experimentalists in, and I was ready to tell them it's not going to work. Before I said that, they told me it was working. And this was the reason. We were actually seeing this, this carrier modulation. Okay. We can do some pretty good imaging with that. Here are a couple of inclusions in an acrylamide phantom. They have acoustic contrast, but one of them has very little optical contrast, one has a lot. And you can see, maybe in the ultrasound picture, you can see the top and bottom of the inclusion. Let me tell you if you can't, they look very similar. And in the ultrasound modulated image, we see just the left one, because that's the one that has the optical contrast. Okay? The signals are there, but they're still weak. They're 4 orders of magnitude below the carrier. Here was some data we collected with different concentrations of milk and water. And you can see the carrier falls off fairly gracefully, and the carrier modulation signal begins very low and falls even lower. About 4 orders of magnitude, typically, difference between those. Okay, what made this work was speckle averaging. Okay, you know that if I collect data in a numerical aperture NA, the speckle size is going to be something like lambda over NA. Okay, and so if I collect a large area and a large numerical aperture, I can have a lot of speckles. In that example, we had about 70,000 speckles. Okay, the individual speckle is going to have a size lambda squared in 3 dimensions, and we're just going to pick up large numbers of speckles and do that coherent averaging. And this is actually from our simulation. I took these data points for single samples, single speckles, looked at the statistics, mean and standard deviation. I found that the standard deviation of the carrier was, of the first sideband was essentially 0. And so I did incoherent addition on that, detecting it in a number of different ways, got about the same result. I did coherent addition of the carrier suppression, and I get basically a linear increase with speckle number, and they cross over somewhere in the neighborhood of 1,000 speckles or so. So now the question is, for new work, can we measure the wavefront? All we were doing here was we were looking at the fact that it changes, and we were averaging over lots and lots of speckles. If we want to measure the wavefront, we can't average over too many speckles, right? Because the information that we want is contained in each individual speckle. Okay? So the result is we're going to have many degrees of freedom. We've got to take the signal-to-noise ratio that we saw in the last chart and spread it over all these degrees of freedom. Okay. If we can do that, that opens the door to adaptive optics. Okay? In adaptive optics, you use a guide star, image through the atmosphere, and you correct for the atmospheric turbulence to get a diffraction-limited image of the guide star and of things around it. If we can apply this in tissue, we can do that kind of imaging, correction of the wavefront, but we can also conjugate the wavefront and focus light to a small spot. We could basically move this guide star around and have the light follow it. The question is, how do you get the guide star in? Okay. Just briefly, what happens is in our photorefractive crystal, instead of using the reference beam as the playback, we use its conjugate. And now the image will be the conjugate of the object, amplified by our R star again, and going back this way. So if we pump the photorefractive crystal from both directions, pump 1 and pump 2, one serves as a reference, the other serves as a probe, and vice versa. We generate both the image wave and the conjugate. Okay, here's no ultrasound in this one. Here's a simple little tissue model. I stole this from the skin imaging work that we did earlier. A nearly point source of light propagating down through this material is scattered not so much as in the other material. And now if I just say, let me make a confocal microscope, let me just focus light back to that point, it doesn't work very well. Okay? But if I take the conjugate of this wavefront here at the bottom, it gives me an excellent, strong focus, even through a scattering medium. And I did an easy problem. I didn't do the scattering medium that I did earlier. I'll come back to that though. In addition, I can also use what's called the optical memory effect. Once I collect this wavefront, instead of playing it back, I can tilt it and play it back. And here I've tilted it like 5 microns out of 40, and here even 10 microns out of 40, and I still get a good focus. So I can do some imaging around the neighborhood of the guide star. I can also change the wavelength. Okay, here there's a picture I showed you earlier of the reconstruction. Here's the same reconstruction but done with a longer wavelength. The wave is a little bit bigger because the diffraction limit of this aperture is a little bit bigger. Okay, how wide a bandwidth can I use? It depends on how much scattering I have. Okay, so finally let's try to do something complicated. Light source at the top is a plane wave. This red bar is the source. Enters our old scattering medium, the same one I used earlier. Interacts with the ultrasound, comes back to this black line, which is the detector just below this source. I cheat and turn the source off so that I can measure the returning signal at the detector. I can use pulse light, or I can use a long pulse and let it come to steady state. Okay. Here's the probe sideband. Scattering, a fair amount of it scatters out the top. And if I collect that light at the detector and conjugate it, I get a half-decent focus. If I do the same thing with the carrier suppression, this time in this situation, not so good. Okay. One of the things I want to point out, if you look at the wavefronts, this is the curvature of the wavefront for the different modes. I have it better on the next slide. Okay. Each of those waves has a pretty well-defined curvature. There's some information coming back there. The light is not completely disordered. Just want to give you a sense of the relative amplitudes, how much the light is reduced for each of the sidebands. But the point is, there is some order. How do we measure that order? I'm running short of time, so just briefly, we're using something called the Wigner distribution. And what it does is it measures both the position of the light and its distribution in angle. Position is measured horizontally. Distribution in angle is measured vertically. This linear slope indicates a general wavefront curvature. Okay? If I take the derivative of a parabola, I get a straight line. So that parabolic wavefront curvature is represented by this. The spread in this direction is representative of the scattering. If there were no scattering, if we were looking at a diffraction limited wave, the width of this in the vertical direction would be inversely proportional to the width in the horizontal direction. Okay? By diffraction theory or by the uncertainty principle from quantum mechanics. Okay? So an area in here corresponding to 1 lambda over n represents 1 speckle. Okay, in this case 532 nanometers divided by 1.33. If I look at the weighted area here, I come up with about 10.4 microns, about 26 wavelengths in the medium. Okay, and if you compare that to all of the data that I can collect, it's 200 wavelengths. So there's still 200 real wavelengths, so 260 wavelengths in the medium. So actually, the randomness here is only about 10%, even through all of that scattering. There's still a lot of information here. And what we're trying to explore is different ways of using that to construct the conjugate wave. Okay, so briefly to summarize, we've developed an FDTD algorithm, verified it against some previous work. We found that light traveling through scattering media still retains some order. And we found that we can use an ultrasound guide star to image in highly scattering materials. We may even be able to use optical memory, and it certainly will help us reduce the number of degrees of freedom. There's a trade-off between using the sideband and the carrier suppression, which we're still working on. We think that this may give us a technique for delivering light into tissue exactly where we want it. And we're going to be looking at other models because we recognize that this small model can't be expanded infinitely. It takes 2.5 hours to run on the computer now, and it grows very rapidly as you increase the size of the problem. Okay, so if all of this works, my hope is that we can do this. I didn't get that to work there. In any case, I'm running late. You get the idea. Can we make order out of the disorder and bring everything back again? So with that, I thank you. I want to acknowledge my teammates, and if there's time, I'll be willing to take questions. I am extremely hard of hearing, so I've got people up here in the front row who are going to try to help me with the questions. Thank you.